Hey everybody, I'm talking about Lustre 216 and beyond today. We're a few days short of the actual 215 release, but so I'll mainly focus on what's coming up beyond that. So here's a brief list of features that we're working on. There's sort of the major features. There's always going to be ongoing work that's small improvements here and there. But the major ones, unlike Peter, I did mention the IPv6 that James Simmons was asking about. So that's in here, directory traversal in 217. There's already a number of features that are starting to be worked on, data compression and write-back cache in particular. The erasure coding is a little bit stalled right now. We don't have anybody working on it. There's some, it's about, partly done work. And there's early discussions on what we can do to improve Lustre metadata redundancy. And I'll get into some of those detail. So in 215, there's been a number of improvements in terms of handling multiple sockets in TCP. We found that single socket communications are bottlenecked on the CPUs. And so by having multiple connections per peer, as we did previously with InfiniBand, you can also do the same for TCP. And so this is actually being auto-tuned now so that you get a pretty good performance, 100 gigabit NICs and 200 gigabit NICs to 4 connections per peer by default. And that improves the performance quite significantly. As you can see, almost double the performance. The LNet selection policy allows tuning on NUMA systems and systems that have, non-uniform multi-rail. So for instance, IB and TCP, you could say, only use IB unless it's down, various things like that. Upcoming in 216, Neil Brown from SUSE has been doing quite a bit of work together with James Simmons on IPv6, and a lot of the infrastructure went into 215. Addressing support and a lot of the data structures internally are already converted over, but the external configuration of IPv6 peers through Lustre and normal configuration logs still needs to be done. And in order to help that along, there's work done to simplify the remote node addressing so that, for instance, we can hopefully get rid of storing NIDs, IP addresses directly in the Lustre configuration logs at all. And this would be, done dynamically through the MGS. And so the servers would, when they mount, they connect to the MGS. And the MGS reports their, available interfaces and failover peers and things like that directly to the client. So the client configuration log doesn't have NIDs stored in it at all. And that not only makes it easier to, have dynamic addressing, if you have, well, heaven forbid, DHCP on your servers, but also, you're able to mount a target on any server that can access the storage, and then you don't have to pre-configure the NIDs. And so that should simplify the administration. On the client side, there's ongoing improvements, and Patrick Farrell will have, a presentation on the details of this. Just at the high level, RDMA memory access for GPUs is interesting and pretty relevant these days, so that You know, Lustre could always do RDMA, but now we can do RDMA directly into the NVIDIA memory. And so there is some work also ongoing to make this more generic, but right now it's only the NVIDIA GPU Direct. But hopefully that will expand in the future. And in 2.15, there was quite a number of direct IO optimizations. And, you know, Patrick gave a presentation on that last year. There's a new presentation for work that's being done in 2.16 about buffered and direct IO performance improvements that I won't cover here. There's ongoing code cleanups, you know, in the InfiniBand code layer to work with the in-kernel OFED. Lots of structure cleans ups. This is kind of an ongoing goal from Oak Ridge to, you know, really sanitize the code and get rid of old cruft that's existed. You know, Lustre first, you know, added, I think, support for 2.4 kernels, you know, 20 plus years ago. And so a lot of that stuff is getting taken out. And of course, it's, you know, it's an ongoing, not a battle exactly, but it's a treadmill of keeping up with API changes in the kernel itself. Because the kernel development style is there is no such thing as a static, you know, API. If people want to change things, they change it, and it's up to us to, you know, adapt or die. Similarly, on the back end side, there's a bunch of work that's being done to improve backend storage performance. In previous releases, we did E2FS CK parallelization for pass 1 and 5, which was inode scanning and block scanning. And now, because we've, you know, optimized away, you know, the 90% of the time now, what used to be a small fraction of the time, it's Amdahl's law, right? What it used to be the small fraction of the time in pass 2 and 3 is now the majority of the time that's spent in E2FS check. And so, you know, we're looking at what can be done to parallelize that part of the code as well. You know, it was mentioned earlier as well about ZFS DRAID. That's available in ZFS 2.1, which will be the default, you know, version that's being tested in the next release cycle. Arshad from Aon is working on fallocate for ZFS. I missed the feature freeze for 2.15, but will be in 2.16. And LDiskFS MBAlloc is actually work that was done in upstream by Google, which is, you know, always nice that Google is devoting a lot of time and effort for ext4. And similarly, another upstream project, which is ODiscard efficiency. That's for automatic trim of flash storage, so that you can, you know, the flash storage can internally optimize the erase blocks. And up until now, I mean, this code hasn't landed in a Lustre release because it's only in the newest kernels. But we're looking at backporting it, just because the current mode for ODiscard is pathetically bad, and so I wouldn't recommend anybody to use it today. And the other option, FS trim, which is sort of offline, or not exactly offline, it's online trimming, but it's manually invoked and it runs, you know, on the whole file system. And the goal of the ODiscard is to continuously sort of trim in the background as space is being deleted, right? So it doesn't have a big burst of work to do, you know, if you run it every few hours or every day for the FS trim. And then finally, you know, OSTs are getting pretty huge, right? We regularly have OSTs in the 500 terabyte range. now and getting up to 1 petabyte, and that, it used to be a whole file system, and now that's one OST, and they still only have 32 directories per MDT, and so it's stretching the limits. And the part of the issue is that if we make this 64 or 128 directories per MDT, it doesn't significantly help the problem, which is that the object IDs are inserted into a directory, essentially in a random location because it's the hash of the name. And so having more directories, it's the same total number of objects, spread across the same number of blocks, and that's just random IOPS. And so what we're doing is changing the protocol a little bit so that essentially you age out the object directories over time. And so older objects, get relegated to older directories, and then they can just drop out of cache because they're not being accessed. And then you'd have smaller directories for the new objects. And so it's code that's ostensibly always existed. It just needs some fixes to get working, and so that's well underway. And yeah, I can't. Maybe I could bring up the question Q&A. No questions yet. I didn't have the Q&A up on my screen. Another metadata improvement is cross-directory stat ahead. And so this is sort of laying some of the foundation for the metadata write-back cache. And essentially what's being worked on here in this feature is batched RPCs. And so that allows a client to send multiple metadata operations. Get-attr is quite easy because it doesn't change the state of the server. And then right now we do have, for ls-l or find and things like that, there is already stat ahead, but every stat is sending a separate RPC to the MDS and also a separate RPC to the OSS and for each file. And so if we already know that this application is reading all of the entries in a directory, instead of sending thousands or millions of RPCs, we can send a batched RPC that says, get me the attributes for 100 files at a time. And so that's more efficient on the network. It's more efficient on the servers to process these. And then, we can also use this infrastructure for the write-back cache, and I'll explain that in a minute. And so in addition to the normal ls-l stat ahead, which has existed for a while, there's a new cross-directory stat ahead pattern, so that it can distinguish between a breadth-first search, going across all of the direct files in one directory level and then working its way down, or a depth-first search, which is descending to the bottom of the directory and then reading all the files and going up one level and then back down to the next directory. And so these cross-directory stat aheads can help, if you're doing ls-lr or find, it can start prefetching attributes from a different directory than what the application is currently looking at. And so this can help, especially with smaller directories and, more dense trees rather than just the large, many files in one directory case. And it has, both the breadth and depth first searches. It can distinguish right now, stat ahead only detects if you're doing the stats in read dir order, right? Which, appears random if you look at it, but it's the order that the files are stored on disk. And it will also now detect if you're doing a pattern of, reading and statting the files in, alphabetical order, right? And so it can optimize this case a few different ways. So the metadata write-back cache is going to extend on that. So this is more of a 217 kind of feature. There's quite a few patches. That is quite a lot of work already done here. It's just sort of crossing the T's and dotting the I's to get integration of write-back cache with things like quota and space management. And the goal of, the overall goal of write-back cache is to allow clients, to create files and directories directly in memory without sending any RPCs to the MDS. Like right now, every directory you create, you send an RPC to the MDS to check that it doesn't exist yet, etc. Every file you create, it needs to do the same thing. And so that adds in, a network round trip latency for every file operation that you do. And so what write-back cache will allow you to do is, you're untarring a file. This is common in genomics. They, have a tarball that's contains all of the snippets from the genes, and they untar them into a directory for every job they run. And we can reduce thousands or millions of MDS round trips to get better performance. The other important thing about write-back cache is that it's coherent with so it's mainly targeted at newly created directories or directories accessed only by a single client, but it also has to be coherent across all of the namespace as well. And so when a client is creating a new directory, it would get an exclusive lock on that until there's such a time that there's contention with other clients, or the lock ages out or gets f-synced and things like that. And so the good thing about write-back cache optimization is that it's totally transparent to the applications, and you won't have to flush the entire tree if there's any kind of contention. It essentially it flushes the cache from the top down in the directory tree, and then if a client is accessing some specific path, only the directories that are relevant to accessing that specific file would get synced out, and so you don't have to wait potentially a long time to flush out the cache if there's megabytes or gigabytes of data there. And so, like I said, the code is very advanced in terms of development. It needs testing and review. Of course, if there are people who are interested in this, giving it some testing and reviewing of the code is always welcome. And Steve already had, there's other D&E improvements. Steve's presentation was covering a lot of this about the space balancing and thing, and I think this is one of the main areas where D&E has had a shortcoming previously. And so I think what's in 2.15 is really a big step up from what was available previously in terms of using MDTs coherently across a whole file system. And I do agree what Steve was saying, that there's still work that can be done to improve the heuristics. I mean, we've been a little bit reluctant to enable this for every directory all the time, just because it's relatively new work. And the great thing is that HRT is really been pounding on this feature, and we're finding out where it breaks down, and that can be addressed, I think, pretty straightforward ways. And I hope that everybody can get a benefit from this in 2.15. 216, I already mentioned the object directory scalability. That's sort of an interchange between the MDT and the OST. So they need some changes on both sides. And there's also work already done, just waiting to land on optimizing the D&E locking and distributed transactions. And that's because more, with the space balancing, more of the operations are on remote MDTs. And so, optimizing the performance and, improving the, times that MDTs need to, process recovery logs and things like that is important going forward. And let's see what else. So the new topic that I've started working on, getting some architecture and understanding what needs to be done here, is Lustre metadata redundancy. And so, since about 2.12, I think we've had a file level redundancy, and that's working fairly well. It's had some issues that are being, that have been worked out, and most of the fixes I think are in 2.15. But the metadata redundancy is something that really needs to be addressed to make Lustre more robust, in a variety of environments, cloud and things like that, where you really need to depend on file system level failure management rather than storage level management. So this is going to be a fair amount of work to be done, and so it's being split up into a number of stages in terms of development. And with everything in Lustre, I tried to make sure that each of the incremental stages is providing something useful, because we had in the past, there's been a number of times with gigantic projects that take 2 or 3 years to complete, and if they don't track and get code landed incrementally, it makes the amount of effort to get the feature landed at the end overwhelming. And so the first stage of the metadata redundancy is looking at services that are dedicated on MDT0 and seeing what can be done to distribute those or make them fault tolerant so that other MDTs can take over, right? And so one of the critical functionalities of MDT0 is the FID location database, FLDB. And so that's really the core data structure that tells clients and all of the servers which FID sequence ranges are managed by which servers. And today MDT0 is the primary FLDB server, and it's the only one that's guaranteed to have a full copy of the FLDB. And so while it's that database is not very big, really it's only 1 or 2 lines per target, right? It's so even in huge file systems, there might only be a couple of thousand entries in this table. But really every MDT and OST already has some fraction of this table that it caches locally. And so the incremental work to have it stored on all of the servers all of the time is not very much effort. And because it only is being updated hardly ever, right? It's usually just when new targets are first formatted and mounted the first time they get a new entry. Each sequence range is 1 billion sequences, so that is quite a lot. And even with the like I was saying, the OST directory scalability, where the MDTs are going to be, going through sequences more frequently. That's still, tens of trillions of objects. We're not going to run out anytime soon. MDT0 is also the quota master. And so it, manages all of the user group project quotas, OST quotas centrally. And, that needs to be able to migrate off of MDT0 and, split it up across multiple servers. There's no reason why, we can't have, quota ID 1 is on MDT1 and quota 2 is on MDT2, et cetera, and split the load because they're totally independent, right? And so that's relatively straightforward. FLock locking is managed entirely on MDT0. So we need to look at, this one's a little bit more tricky because FLock has to have deadlock detection. And so it may be more tricky to, split it up by FID or whatever, because you don't want to have circular deadlocks in your FLock. But, maybe it should be possible to, run it primarily on a different MDT, mainly because MDT0 is already doing a bunch of things. And, having it just, pick up on any MDT that's available, or MDS, I should say, really, allows distribution of the workload. I'd previously mentioned this one, improving D&E metadata, distributed transaction performance. This is, it's important, just to get D&E distribution, more scaling, better recovery, and things like that. So some work has already been done and waiting to go. The other one is that the Lustre log structure is good for some types of workloads, but it turns out that it's actually one of the issues with the D&E recovery that's more complex than it needs to be, is the use of the LLog, because it has single bit updates, and it's hard to do a transaction for updating one bit in the file system. And so we may look at a different data structure for the distributed transaction logs, and that should simplify a number of things. And it also removes the need to do synchronous updates in a distributed transaction. And so this is good for today, and it will also help the distributed transaction performance for the case once we start doing things like replicated directory updates, so that every make dir, every file create could potentially be replicated onto multiple servers. So we really need the performance of distributed transactions to be improved. And the final one that I'll talk about today for the LMR is getting the basic replication done for top level directories. And so right now, root is on MDT0, that's how you find it. And it has, all of the top level directories, which is typically not very, many. There might be, tens or maybe hundreds of directories at the top level of the file system, sometimes even just one or two. But, if MDT0 is offline, you can't access the rest of the file system. For other MDTs, you could isolate it potentially, subdirectories being specific to a single MDT. And so if, MDT7 is offline, you can still access directory trees that are on the other MDTs. But if 0 is offline, then you can't go through the root directory. And so because there's very few entries there, and because it's updated, relatively infrequently, replicating the top level directory should be pretty straightforward. You know, we already have the distributed transactions, so it shouldn't be have a significant complexity in terms of of infrastructure in the code. What does need to change is some of the on-disk representation. So for instance, a directory entry needs to have, you know, multiple FIDs in it so that you can look up a name on two different, you know, MDTs and then access either of them, you know, to get to the next subdirectory level, right? And then, you know, we have to decide on things. How many replicas do we allow? 3 or, you know, 7 or something like that? You know, is the initial, I think the initial implementation would, you know, not let you modify the root directory if MDT 0 was offline, but from most, you know, use cases that I can think of, that shouldn't be a huge limitation. You could still access directory trees that are on other MDTs in that case. And then, of course, you know, we need to add in tooling for LFS, you know, set dir stripe, find, and all of those things, LFSCK, and you know, later phases of LMR, which I won't get into today for time limits. Later phases of LMR, you know, extend this into, you know, replicating, you know, subdirectories by policy, then replicating the file entries, you know, inodes across MDTs based on performance and things like that. And you know, so it's going to be a few releases down, but I think it can be, you know, provided in a way that delivers incremental functionality in each stage. And with that, I'll go to questions, I guess.
All right, thanks, Andreas. We do have a couple questions. So first one is from Nathan D. He asks, will metadata write-back caching be enabled by default, or is this a feature that you would only turn on or use for specific workloads?
I think, you know, it depends on you know, a little bit on our confidence in implementation and, you know, performance and things like that. But you know, my goal would be that it's on by default. You know, you could have a tunable that says, you know, don't use it on the MDS if there's an issue with it. The good thing about write-back caching is that it doesn't change any of the on-disk formats or anything like that. It's essentially just a delayed delivery of requests to the MDS and, you know, locking changes in memory. So there isn't any persistent changes to the file system, you know. So if there is a bug in write-back cache, you know, rebooting the client would get rid of it, right? So I think it would be enabled by default. There's kind of two stages. One is for new directories, right? So every time you create a new directory, you get an exclusive lock on that on the client, and then the client can go crazy and create whatever it wants. And so for, you know, untar, or, you know, not that this is benchmark specific, but if you think, you know, MD test directory per process, you know, those kind of workloads would work very well with write-back cache. The next stage would be using write-back cache for existing directories. So essentially at that point, the client has to get the exclusive lock and then read all of the directory contents into its memory so that it knows which file names exist and which don't exist. And then it can, you know, write-back cache new updates into that directory. And so whether that's enabled by default, it, you know, is really a heuristic on whether it's performant or not. So I hope that answers the question.
Okay, and one last question. This is from Stefan Thiel. I understand WDC is using local node memory while PCC uses local node storage. Other than those differences, could you elaborate on how WDC compares to PCC?
Yeah, so the difference, the write back cache is for metadata write back caching. We already have data write back caching, write aggregation and read ahead and things like that for the data side. And the write back caching is for the metadata. And PCC is, again, it's right now, it's only a data side optimization. And so you still have, PCC will write, make a copy of a file into a local flash device, but you still have to open up the file on the MDS every time you open the file, right? And so that's how it knows that there even is a write back cache or a PCC copy of the file. It stores a layout in the file that says there's a PCC copy. And so there is actually work being done to integrate those two so that, a write back caching client can write the data in memory for a file, and it could spill into PCC while it's waiting to flush data, to the MDS and the OSSs, or if you have a very, IOPS intensive workload, when you want to write files into local storage rather than sending it over the network until it's, your IOPS heavy phase is done. And then it would, write it out serially to the OSTs, right? So there is some work to integrate those, but, the first phase of the write back cache is they're targeting two different areas of the code.
Okay, and Stefan had a continuation for this question. So will WDC also use HSM states?
I'm not sure about the answer there. I mean, the write back cache is really only in memory. And so it's not going to be, changing the layout to the file like HSM or PCC does. But that doesn't mean that the state machines for managing what's present and what's not present won't have some interrelationship. But right now, all of the write back caching is only controlled by the DLM blocking because it's all done in memory.